Today's talk is about NVMe in the real world and how does Facebook use NVMe. So let's start off with Facebook. Facebook's mission is to give people the power to build community and bring the world closer together. And now let's look at Facebook at scale. Facebook now is up to 2.7 billion users. Messenger up to 1.3 billion, and 1 billion Instagram users. In this picture, you can see one row in one data hall. It's filled full of servers, networks, storage, flash, and our goal is to give our users the optimum user experience, which clearly involves using lots of flash. Now, let's look at, here are some pictures of some of the data centers for Facebook. You will see, as in terms of scale, that these are roughly 4 football fields in length. Oftentimes they are shaped like an H, where there are 4 data halls with an adjoining piece between them, which is very useful for offices and other things. So they're very massive and large. Now, NVMe. So we'll start off, why NVMe? So if you look at this picture, in hyperscale, we require the IOPS to scale with capacity. So the IOPS per terabyte need to scale linearly. And as you can see with NVMe, it scales very well. And with SATA, how the IOPS fall off. Thus, this is the driver for why Facebook uses NVMe. Now, let's talk about some of the things going on in NVMe and the benefits associated with those things. Deallocate. There are challenges and improvements. So let's talk about this. So how is it good? It's good. It's a hint from a system. It allows you to know how to garbage collect. It reduces write amp. And it improves performance and endurance. What's the challenge? Oftentimes when doing this, there's latency spikes due to the deallocation, blocking the reads and writes. Obviously, nobody likes latency challenges. So the old solution is we tune the system and for each supplier and try to find the optimized setting. This is a challenge of, well, which supplier do I tune to? How do I decide what those settings are? When I go to the next generation of drives, do they have the same settings? There's a challenge to figure out how to do this. The solution in NVMe 1.4, it allows the SSD to advertise its preferred deallocation size. By doing this, it allows the system with an optimized standard mechanism to advertise how we would like data to be deallocated. Next challenge. Managing at scale is a challenge. With lots and lots of equipment, obviously, there are lots of things that can happen. The first challenge is restricted access. There are no vendor-unique tools. We cannot have vendor-unique tools in our data center, and thus we need standard mechanisms. There is NVMe CLI. This allows access for us to get all our data out of the drive in our smart logs in a common format. So though many vendors may have vendor-unique things or things placed slightly different, it allows a standard way of reading everything out. NVMe CLI is open sourced, and there's a link here for you. The next challenge with this is, suppliers would like to debug their drives, and how do they debug with no physical access? And the answer is telemetry. Telemetry allows a standard way of pulling debug data off the drive that suppliers can use, so that now we have a standardized mechanism of debugging drives in the data center with no physical access. Next challenge. There can be many challenges where the amount of data written to the SSD can exceed the endurance for the SSD. And given the expected lifetime of the SSD, it can wear out. So let me give an example of this. Say I have an application that needs 250 gigabytes of data on the drive, but it will write using the entire SSD capacity. In this case, this may be a very write-intensive workload where it will wear out the drive despite having a high number of drive writes per day. So what can you do? There's a namespace management command. So by using the namespace management command, I can take a 512 gigabyte drive, configure it as a 256 gigabyte drive. Now the application sees 256 gigabytes. However, I have twice the number of drive writes per day because I've reduced the capacity that it's seen by the application. Next challenge. We're doing performance testing. We're doing lots of trim. And how many blocks have data in them and how many don't? And how do I understand that? This is a challenge in understanding because we're doing lots of writes, we're writing lots of trims, but how much free space do I really have? And that's not clear. The solution is namespace utilization. It allows us to determine the number of LBAs that actually contain data. Next, now we're going on to more challenging topics here. So security, as you all know, is a very important topic in the industry. There's been lots of discussion about that. NVMe Express supports secure send, secure receive. Lots of great stuff going on with security. There's even an open source tool for NVMe Opal that you can use to implement security. And along with that, secure boot is a very common industry feature. Secure boot allows you to ensure that the firmware running on the device is from the supplier and not some other source. That's all great. Now here's the challenge. There's no industry standard way of determining if secure boot fails that secure boot failed. The drive simply doesn't work. And so I'd encourage the industry to consider standardizing secure boot failures. And so there's a common method across the industry to know when this happens. So with that, I will let Cameron take over.
Okay.
Thank you.
All right. Before we bring up Lee Prewitt, so just a quick show of hands. How many of you are using NVMe SSDs today? Wow. I probably thought it'd be a little bit more than that. Okay. Well, and then just seeing Ross's slides here. How many of you were familiar with Facebook's data center setup? Yeah, I think it's fascinating. What both Facebook as well as Microsoft and some of the large hyperscalers have as far as configurations. Their data center configurations. Actually, a lot of those look pretty the same architectural, obviously by design. So I'll bring up Lee in just a second. But again, if anybody does have questions for them, we can address them right at the end of Lee's speaking session here. This is going a little bit faster than I was expecting, so maybe we'll run through it again. For our next presentation, I'd like to introduce Lee Prewitt. Lee is a principal hardware program manager with the Azure CSI group within Microsoft. He's been with Microsoft for more than 11 years and has deep technical experience in both hardware storage and software. Lee is also active board member and Microsoft representative on the NVMe Express promoter board of directors, and a primary contributor to many aspects of the NVMe specifications. He goes far back in storage, writing a Mac SCSI driver back in 1991 for a 650 megabyte Sony magneto-optical drive. So how many of you are familiar with MO drives? All right, that's about as many hands I would expect. Definitely the younger crowd may not have any idea what that is.
Gray.
Yeah. Lee looks a lot younger than he apparently is. And best of all, he brews his own craft beer. So we'll have to get a rundown on what he's brewing at the end of his session. Please provide a warm welcome to Lee Prewitt.
Okay. So, time to talk about NVMe at hyperscale. I'm going to retread a joke that I used this morning that basically was in the track that Ross and I did this morning, where he went first again, and I went next again, and so the idea is like what Ross said, and I can just kind of drop the mic and we're all good. But that would be even shorter than the shortest program we have all today, so I guess I won't do that. So kind of want to talk about, here's kind of what I'm going to go and run through here, talk about some of the things just like Ross's was, like talk about our Azure as it stands today, why we're using NVMe, and then some of the issues that we see around the devices at scale and what NVMe can do to help with that. So, kind of thing, here's the speeds and feeds that we talk about for Azure. I can let people look through this, through some of the things, but really at the end of the day, it's the one over there on your right, that's millions of servers. And so with that, most servers in our data centers have at least 6 NVMe drives in them. So if you think about millions of servers with at least 6 drives, you're talking millions and millions of NVMe drives being used in the data center. So why NVMe? You can talk about this through the trend focus kind of data that I'd gotten a little while back, and talking about the projection around all these different things. And we're talking, these are exabytes, right? And so the idea of hard drives are still there. They're still growing. We're still going to be using them. They're still something that we're going to need to use, but the idea is that they are going towards more colder and colder data. Then we have kind of the NAND exabytes here as an also trend line, as you can see that, and that's growing explosively as well. And so around that, the idea of hey, fast NAND for hot data, maybe TLC and QLC for cooler and cooler data, but that trend is going up exponentially as well. Sure. So I'm going to talk about a few slides here around some of the issues that we see. Now, this one's not necessarily an NVMe issue. It's maybe more of a form factor issue, but it kind of informs some of the things that I have in later slides about some of the things we want to drive for within NVMe. And so with this is kind of something of some of the things we were seeing with M.2. We basically had an issue in the data center where a PCB for the M.2 is quite thin, has quite a few layers. And we ran into a problem where we had a lot from a PC board manufacturer where their TSVs were a little bit off. And it was such a minor thing that during the certain power on and the testing at both the factory and the system integrator, everything was fine. But around about 10 power cycles, which is about just enough to get into the data center, those TSVs would basically open up and the drive would die. And so around that is kind of like at scale, if it can go wrong, it will. And so the idea is that what can we do in the data center that when weird and wonderful things go wrong, how can we catch them quickly and get the information back, not only to Microsoft, but to the IHV who supplied us that part. So maybe we start some of the things with the issues here. So you can see some of the initiatives that Microsoft is doing around their data centers and data center ideas. This is a prototype system that we did where we actually took and we put a bunch of servers inside a waterproof container and sunk it in the ocean. And so the idea here is that, hey, we have cooling for free, kind of, but if something like that TSV issue happens in that, it's sort of hard to send a diver down there with some parts to go inside and fix it back up, right? And so around this, we're trying to think of things that not only from an issue standpoint of view, but from control and usage and workload, performance, endurance, and how do we use some of the things in NVMe, such as the endurance group monikers for a device petabyte written number and its wear out factor and that sort of thing, where we can basically over time, and we're looking at, because these things are, say, sunk in the ocean, we want to be able to use these devices for I know we have about 3-year warranties, but we won't talk about warranties here. But the idea is that, hey, we want to have that lifetime of that device be 5 years and maybe even 7 years in the data center. Because that's kind of the scale of the timing at which we start to move around and take out older stuff, decommission it, put in new stuff in the data centers, we think. So it's like, hey, this thing might sit there 5 to 7 years at the bottom of the ocean. We'll pull it up, clean it out, put new stuff in it, and put it back down. That sort of thing. And then, talking about some of the things around QLC, that's where we see zone namespaces as being very important. This is the one that's being worked on in NVMe right now. The idea of basically taking some of the aspects of shingled magnetic recording and being able to put them on an SSD such that we write to it sequentially in very defined, well-defined chunks. And then we can read it randomly, and then when we're done with that data or that zone of data, we can reset that zone and the bright pointer goes back to the beginning and we start all over again. And so around that, we can really, we feel with that, we can minimize garbage collection, or minimize WAF, maybe close to 1. We can do things around, since it's a zone and we're doing large writes, minimizing DRAM for L2P tables, so we can do a larger indirection unit and that sort of thing. And oh, by the way, hey, maybe we can also win with reducing the over provisioning down so that we can use all the device, which is nice. So again, it's back to the same picture. I'm sorry I couldn't come up with another picture that would work very well with that, but the idea of remote debugging. Right? And so around that, in the sense of, again, hey, there is a problem, something's going on, and we want to be able to get to that device, figure out what's going on with it, and then be able to hopefully figure out a cure for that. That's something either around firmware fix, or hey, maybe there's some actions that we could take, say reformat the drive or things like that to bring it back to a healthy state. Right? And so some of those things that we're really interested in, timestamp. That's the idea of that when we power on the drive, we'll give you the wall clock time. And with that, obviously, you'll know how long you've been off, which hopefully was very short. But around that, then, if you have events that are happening in the drive and we're doing interactive event monitoring and AENs, you can give us back that timestamp and we can correlate that with things that are happening in the OS at the time. So if the OS is having an issue, the drive's having an issue, they might both be having an issue because they're competing with each other on something. We want to understand that and figure out that timing. And then around this telemetry, telemetry is a really big one. The idea today, Windows has since 2012 or 2016, Windows will actually, if the device doesn't give me the data back when I do an in-page error or an in-page from the memory manager, we'll do a bug check and do on an in-page error bug check. And with that, we will actually go out to the device and say, hey, you didn't give us our data back. Give us your telemetry right now. What was happening in the drive during that event so that we can get that, store that, and at some point through a processing, we can get that to the IHV so that they can debug what happened in that event. We're now in 2019 and onward, we want to expand on that. There's things around where, hey, what the device has a panic or something's happened in the firmware. It would be a great time for us to know about that. So the device will give us the device initiated AEN for telemetry. We'll see that. We'll go out and collect that data and we'll store that. And through processing, we can then get that again back to the IHV. And so around this, it's kind of some of the things around, hey, you gave us 1 million drives. How many terabytes of data do you want back a week on those drives, right? So it becomes a very interesting feedback mechanism for you guys to get back things that are happening at scale in the data center with your devices. And smart. And so that's kind of where we have, of course, the standardized smart stuff. We use that extensively. We also have, obviously, some vendor unique stuff that we've put together. We'd actually like to kind of start to standardize on some of that as well. So I know I've been in conversations with many of you about that, how we can do that and regularize what's happening with all of that. Now, the big one on this is we talked about hey, telemetry and it's all your debug information and all that thing. The really big caveat here is nothing can leave as Ross intimated, nothing can leave the data center that's not human readable. right? And you can understand on that aspect that our security folks are some of the most paranoid on the planet. I can tell you, I've been dealing with them now for 11 years. And around that, anything that we were going to give to you, we have to kind of look at it first and say, oh yeah, everything's fine here. This is not so-and-so's credit card information or somebody's cat pictures or something like that. It's got to be, this is the real stuff that's happening on the drive and how that's marked out. Now, we understand that's kind of a, shall we say, a big ask in some aspects, but we'd like to try and figure out creative ways where we can do things around, maybe there's fine-grained error codes, you give us the decoder ring for those error codes, and so we can say, oh yeah, we know that's error codes X, here you go, can you guys tell us, now, we're now hitting 10,000 of those every week, can you tell us what's happening? That sort of thing, right? So I think these are all ones on the security side. Ross hit many of these as well. He is talking about Opal. Windows is a little unique in this aspect that we also then require IEEE 1667. On top of that is our kind of secure style. Hardware root of trust, things around the secure boot, and again, signed firmware as he talked about. And we actually have also beyond this that's coming on, we actually have a security chip that we're going to be putting on all of our motherboards called Cerberus. Cerberus has the ability to basically interact with any device that has firmware on it, and it will not allow the system to boot until it's actually interrogated the firmware on all those devices. That's on the GPU, that's on the BIOS, that's on the storage firmware, that's on the touch controller, on a laptop. No. But you think of that, any kind of firmware-bearing device, we need to ensure that that firmware is what we think it is. It's our golden firmware, and it's signed properly. So that's a thing that we want to talk to people about, being sure that their devices can interact with Cerberus in a fine-grained way. And then kind of around what we call device hardening. And this is just more kind of the SDL, as they say here, is kind of the software design life cycle. How do we talk about, hey, what's your coverage in, say, Coverity, or what's your firmware code review process? What have you done around pen and fuzz testing and that sort of thing to ensure that the firmware on the drive is hardened as possible against attacks? So with that, I probably could have talked slower, but I didn't, but there we go. So hopefully lots of questions.
Very efficient. Thanks, Lee. Okay. Now, we'll get into the Q&A in just a second. So if you have some questions, please just get them ready. But I just want to ask a couple of questions to these gentlemen here, if they're okay to answer. As far as like applications, right? I know Facebook created RocksDB. Are there any other types of applications, and why RocksDB, and why? What are the characteristics about it that you could not find in other applications? Is that something you can address?
Most of that I can't comment on here today.
Okay.
I mean, obviously we have lots of different applications, and some are performance sensitive, some are latency sensitive, and they have different characteristics. But
so you have different applications for that
Yes.
service different requirements.
yes,
So the range can be performance, it could be latency, it could be
performance, latency, capacity.
capacity, scale.
So.
Okay. Lee, similar.
Right. Well, okay. On that, so Azure is pretty, it's kind of split brain on this, a little bit schizophrenic. So in the sense of we have obviously there are other client groups, but the two major ones are Azure Compute and Azure Storage, and their needs are very different. In Azure Compute, the idea is that at each VM that we're being hosted on our systems, each VM gets about 90 gigabytes of ephemeral storage. And by ephemeral, I mean it's not resilient, power loss or failures or things like that. It's just basically meant as high-speed, local, on-node scratch space for the VM. And so with that, we need the device capacities aren't quite as big, 1, 2, 4 terabyte. You put that on the node, and then the ability, we then chop it up and give VHD to each of the VMs for that scratch space. But the SLA on that is fairly high in the sense of with that, we actually spec out shall we say, it's a little bit of a strange metric, but it is what it is now. And so that's a 8K IO in size and the each VM is guaranteed 4,000 IOPS of that 8K and that 8K can actually be 100% read, it could be 100% write, or any ratio of mix in between, and we have to be able to satisfy that. Because it's kind of funny, these guys are paying for this, and they actually do benchmarks on us to make sure that we're doing what we said we were going to do. So that's the one side of it. The other side of it, Azure Storage, it's all about capacity and cost, right? So it's like we need capacity at the lowest possible cost. And with that, there's obviously the idea of we want to be able to take stuff and we want to be able to tier it and put it in different kind of storage tiers based on how hot or cold that data is. Obviously, in some of our premium things, we're more flash-oriented, whereas in our colder ones, we're more HDD-oriented. But you can think of things around, especially what we're doing with what we call our F2010 JBOF, where we're actually using the E1.L. We're putting in 16 of those and then cabling that to a head node. And so we're starting a capacity on that at 16 terabytes. So you can think, so the storage densities on that start to get up pretty high pretty quickly. Yeah. Right. And so, and those are all those NVMe devices that are, slotted in there that we're using as we go along. And so with that, it's kind of, hey, today, TLC, we can use those for many of our workloads. QLC starts to get a little bit sketchy. So that's where we're saying, hey, NVMe, do the rescue. We're working on the ZNS spec. Once we have the ZNS spec, that'll allow us to use QLC broadly in the data center.
Okay, great, thanks. You touched on some of the new form factors, EDSFF. There's a multitude of different, varieties of them. I guess as much as you can comment, I'll go back to Ross this time. One of the great things about NVMe is that there's many kind of application specific fine tuning you can do between running over PCIe, the number of optional commands that could be implemented through NVMe. But also form factors. A lot of people are familiar with your standard, U.2, 2.5 inch, and M.2. Everybody's pretty familiar with that. I'm not sure if everybody's familiar with a BGA form factor, which is very, very small, soldered down, 16 by 20 millimeter. And then there's a whole slew of EDSFF and of course, add-in card form factors. Again, this is totally unrehearsed, so if you can't speak about these things, please don't disclose anything that would get you into trouble. But to the extent that you can talk about form factors that are either in use or preferred, Ross, what can you comment about form factors?
Sure, that's a great question. So let me start by saying if you download the slides from FMS, there's an EDSFF section, and I encourage you to download my slides. And if you want even better slides, you can download Lee's slides from that section. Today, M.2 is very, very common in hyperscale. There are some challenges with M.2 ranging from power and thermal and things not scaling very well. And we've done many studies looking at the thermals, and the E1S asymmetrical 25 watt scales very well for power and thermal, specifically low airflow, and unlock all the performance with TLC, QLC, storage class memories. In addition to that, I should add it supports both by 4 and by 8 PCIe. So it works excellent for NVMe propagation throughout the industry, as it's a standard ratified in form factor. And in addition to that, it works for not just storage, but any type of PCIe devices you want for a slot. So with that, Lee, what would you like to say?
So that's the beauty of standards. There's just so many to choose from. In Microsoft, we use quite a big variety if you think about more than just Azure. So think of our Surface and Xbox folks. Surface is using BGA form factor to some degree today, and many of our Surface products. We're looking at things like 2230 and things like that to have removability inside, well, not removable. Basically, enterprises are requiring removable so that they can take the drive out before they repurpose the machine. And so we're looking at, even though BGA is great for Z height, we may need to go back to something that can be taken out so that they can do their proper recycle efforts and things like that. For Azure, obviously, as Ross in M.2, Microsoft was actually one of the folks that drove M.2 about 4 years ago into the data center, to our pain and chagrin in some facts. But it's been done very well for us up to now, as some of the things that we talked about, power and thermal envelopes and things like that, and the number of placements on the NAND is starting to become challenging. And so we do want to move away from M.2. We are currently starting a ramp of use of the E1.L in Azure Storage. As I said, we're using that the F2010 JBOF, and so we'll be using that and exabytes and exabytes of that over time. We're currently still using M.2 in Azure Compute. We'd like to move to E1.S. We're looking at the possibilities of how we do that in our next generation platforms. So hopefully the idea is that maybe one or two variants of E1.S become very large scale, very large quantities across the industry.
Thanks, Lee. So we've been rattling off a lot of kind of acronyms for the different form factors. So how many are familiar with the EDSFF spec and know what E1.L and 1U short, 1U long? All right.
This is where we bring Anthony up for a primer.
Yes. We'll have a guest speaker. Okay, so I think at this point we could open up to questions from the audience. If you have a question, please raise your hand and then or come up to the mic. Better yet, so we can get a good audio recording. Please come on up. Joel Diedrich, please ask your question.
Question for Lee. Your comments about zone namespaces and writing in very large chunks bring to mind immutable stamps that are not well suited to latency sensitive random I/O. Is the customer facing side of Azure, if you want low latency and random access, it's going to be ephemeral, and if you want your data safe, it's going to be slow? Or is there a plan for networked storage of latency sensitive things?
So good question. We see a place for that ephemeral storage. We'd like that to be local to the compute node, so it's very low latency. Mm-hmm. And so those kind of stay with the node and with the VM on that node. If the device is taking a VHD that they're putting into actual Azure storage as their kind of permanent storage space, yes, we want that needs to be performant as well. With that, we're using things like, so today, you can think of our architecture and you can see how it kind of expands into the future. So with the SMR hard drive, what we do is we use something upstream of that, say an NVDIMM or a very high endurance SSD, to be a serializer for the data, right? And so we're getting data obviously at the cluster level. Cluster's about 20 racks. It's probably 40, 50 petabytes of storage in an Azure storage stamp. The idea is that as the stuff comes in from all kinds of VMs and external sources into Azure storage, the front end is kind of serializing that in the different NVDIMM head nodes and taking that and then serializing it out to something like an SMR or a zone namespace in the future.
So what is serving low latency network storage? Do you have an NVMe over Fabrics infrastructure or
no? So everything
or?
From around that, as I say, it's kind of the idea is that everything comes in, it's cached in NVDIMM, and then it's serialized out. But the nice thing about that is that obviously if something's still in the NVDIMM, it's instantaneous, right? Because that's memory latency speeds. But if it's been pushed out to SSD, it's nice even on a ZNS device. The read latencies are very low. Then you can do random reads on a ZNS, right? Okay. So it's just that you have to write sequentially, but you can get all your good random read IOPS out of those devices all day long.
Thanks.
All right. Thanks, Joel. Your name and who you're with, and then speak close to the mic.
My name is Kapil. I'm from Intel. Question about debug flow. I think Facebook explained the debug flow and the fact that without physical access, you have to debug the server. if there are OS crashes or something weird like that, is there a out of band debug flow? And I am also curious to learn when there is a physical access debug flow. When does it kick in? And there is a drive light LED. When do you use that in this debug flow?
Okay, so lots of questions there. So let me answer a few of them. We'll start off with the drive life LED, and it is not involved in the LED flow. There's no physical access. As far as OS crashes and other things, in those cases, the OS will have to be reloaded. And at that point, pull logs or whatever is needed to get the information needed from the SSD. But this all needs to be done with no physical access.
Hang
Wait,
on.
Jay
So-
Sarkar, I'm at Western Digital. Telemetry and debug using the telemetry data featured prominently in both your presentations, right? From the current standard of the quality of in data in terms of the value that it provides, the intrinsic quality that you get out of standard run-of-the-mill sort of SSDs, how happy are you with it? Is it high-value data? Do you find it very useful in terms of applying algorithms or whatnot on top of it? But from the value of the data, is it useful?
You want to comment? Sure. So on that front, I mean, it is helpful. I don't want to say it's not helpful. It is helpful to have that. The issue, though, is that today it's invariably a binary, right? And so the issue with that is then, hey, yes, we pulled that binary, but that binary cannot leave the data center. And so, hey, if our IHVs have to be willing that if they can't get that stuff in human readable form, they have to be willing to go to our data centers at a moment's notice. And that data center might be a fun place to go, like Amsterdam, or it might be a not so fun place to go, way somewhere on the other side of the world that you're going to have to be there and sit inside the data center until we get the problem figured out. And so that's where it kind of worked, that call to action to say, how can we together figure out things that make telemetry useful to you, but readable to us, so that you can get it and it'll go to right to your desk when you get up in the morning, you're having your coffee, and you can look and debug what's going on.
Thanks. All right. Dennis Martin.
Hi, for a question for both of you, actually two questions. You talked about the new form factors, the E1S and L. Are you guys getting those now? And when can I, if I'm just buying my server from my favorite server vendor, when can I get those? And secondly, do you have any goals from the storage perspective of, we want to get to, I'm just going to make up a number here, 40% of our drives are NVMe by the end of this year or something like that. Do you have anything like that with the type of drives you're getting?
You want me to start? You haven't talked.
Great question. Yeah, Lee says I haven't talked enough. So, obviously I cannot comment about what I have right now, but what I can say is if walking around the test floor, let's see. I saw Intel drives running in the Oakgate systems out on the floor. I also saw Toshiba with a demo showing E1S drives running. I saw WD with E1S drive in their booth. I saw Silicon Motion with an E1 drive in their booth. Let's see, who else? There was Bitmicro and NGD. Both had accelerators with E1S out on the floor. Does anybody want to tell me? I saw serial cables with debug equipment for adapters and stuff for E1S. Anybody want to correct me if anybody got left out of this?
So it sounds like you're saying it's real. I guess the question I have, and maybe you don't know the answer, is can I go down to my favorite server vendor who I can buy off the web, and when can I see those parts that I can say, oh yeah, put my server full of those?
I can't comment on that one.
Okay.
So with us today, the vast majority of our flash storage is M.2. eNVMe. So we've been doing NVMe for 4 years now. As we move forward, we want to convert those M.2s to either E1.L for storage or E1.S for compute. We're actually starting to ramp on the E1.L with our 2010 JBOF, as I was saying, and around that when I'm saying ramp, it's basically what we do with a pilot, and a pilot is basically 2 stamps. The stamp is 20 racks. You do the math from there. So the numbers are not trivial, but it's obviously not the scale that we'll be doing once we're in full production, but it's non-trivial numbers now. So E1.L is a real thing. It's there. People are getting them to us, and we're buying them from them, and that sort of thing. As Ross pointed out, E1.S, they're probably ahead of us in that respect. I don't want to comment on that, but obviously, from the point of it, there's lots and lots of stuff on the show floor. How real is it to go and buy it, say, from Amazon or Newegg? From my point of view, I think that's going to be quite a ways off. Right now, there's not. It's a lot of because it is meant to be a data center form factor. It's really being adopted by the data center chassis type things, right? And so it's more when the enterprise guys are going to do something with that, and whether they are going to do E1.L, which I doubt. E1.S, they may. They're one of the ones that they are very looking at fondly, and what they pushed in the standard was the E3, frankly. And so how you see these things in, say, your favorite white box server, don't really know. I'm not sure, because as I say, it was meant to be a data center play.
Right. Okay. Thanks.
Thanks, Dennis. Any other questions? Stephen Wells.
Next question.
So I'm Steve Wells from Toshiba Memory. So this is going to mix a whole bunch of things together, but Anthony gave us a by 8 connector for E1S and E1L. You also have this mix of Gen 3, Gen 4, Gen 5. But at some point in time, it's an interesting question. You also have to deal with a finite number of PCIe lanes that you can wire up to these things. So what are your guys' thoughts on how all this is going to play out between all these different speeds and widths and possible disaggregation or non-disaggregation?
Yeah. How do I want to start with? Do you have a thought? I got to think of how
It's a lot of pieces.
There are a lot of pieces. I'm not sure I can comment on your question.
I can always comment, but it'll be my opinion, not Microsoft's. So on those, it's like, so how do I start? For us, I believe that by 4 for storage is a sweet spot. Gen 3 by 4 now, Gen 4 by 4 in the future as the capacities grow, especially on E1.S. Gen 3 by 4 even though we're using 16 and going to 32 terabytes for Azure storage, since the write rate is fairly low, we don't think we need Gen 4 critically on that. Obviously, we'll want that at some point, but. And then around that, so by 8, I feel is more, again, an accelerator type play. I don't think it's necessarily a storage play.
So then would you have just a general socket that supports by 8 then, and then you would possibly allocate? I don't know, I'm just kind of asking.
Yeah.
There's only so many lanes you can map out, right? We're just kind of curious how that.
And frankly, I don't know at this point. It's too early.
All right, thanks.
Okay. Anybody else have questions from the audience? So one last thing. So you've outlined some of the challenges, that you'd like to see maybe fixes for or some help. Both of you guys are involved in the sausage making that is NVMe standards. Are those being addressed by some of the current TPs, technical proposals in NVMe?
I guess that means I'm supposed to start first here.
Yes.
So my issue with secure boot and having a way to identify if the drive has failed or not, the current TPs do not address.
Okay.
And so I would encourage a group of companies to discuss coming in with a TP to address this need.
So yeah, for us, the big one is ZNS, and that's obviously being addressed now in a robust way. My take is we're probably about a month away from phase 2 exit, and then hopefully we're only going to be in phase 3, maybe a month, maybe 2 months, and so we'll have a ratified thing before the end of year, which is great. Around the kind of the telemetry and defining, I guess what I want to say is like telemetry is a great thing as far as it goes. If the definition for a more human readable form of telemetry were to come in as a TP and something we could put into the NVMe spec, that's great. I don't think it necessarily has to start that way, because maybe you kind of define things better uniquely and then make sure that it's baked for the data center and then standardize it.
Okay. Question. Yes, sir. Your name?
Mike Lux, Sanity Solutions. 2 questions. Number one, I know Alibaba wasn't here, but last year they talked about open channel SSDs. Are either of you interested in those? Number 2 is, what about computational storage? Are either of you looking at persistent memory and moving compute into storage?
Where's Matthias? Is Matthias here? All right. How do you want me to?
You can go ahead and answer
Okay.
that one.
Lots of moving parts on that one. So let me see how I can kind of parse that apart. Sorry, your first question again? Open channel. Open channel. Thank you. Open channel. I personally don't ever see Microsoft doing a full-on open channel drive as it's defined, say, in the 1.3 spec. We did drive an initiative called Denali. That is now ratified from the Denali members. If people want to take a look at that, they need to talk to me. And that's kind of you could think of it. Here's the FTL block level interface as it stands today in NVMe. Here's Open Channel and Open Channel 2.0. There's kind of bare metal on the NAND. Denali, we tried to find a sweet spot in between that. Where, yes, the host gets to take over a bunch of stuff, but it doesn't really have to understand the physics of the NAND. So NAND management is still part of the drive. And we see some aspects around Denali that are very interesting. But with that, what we've done now is we've taken a large portion of the concepts of Denali, and guess what? It's ZNS. So that's how we're standardizing it. We're taking those and pushing that into the actual NVMe standard. Now, again, sorry, the question on the second part was computational storage. Oh boy, that's a big one. So here's my problem. Computation as something either as an NVMe device or a PCIe device, very interesting. Computational storage on the so computation or acceleration on the storage device itself, to me, unfortunately, it's not very interesting, and I'll tell you why. Problem is, somebody's data comes in. First thing we do is we compress it. Next, we encrypt it, and then we erasure code it. And so by the time it hits the drive, it's got a minimum of 3 transforms on it. Then it makes it very difficult for the drive to do anything with it. Now, we had some thoughts around, hey, could we do some things through, say, trusted send, trusted receive, where you get a secure package of, here's all the transforms you need to undo, and here's the payload of what we want you to do with that, and here's how you get us the results back. But that seems like a very heavy lift to do that in the drive itself. And so there's actually one of the things that's been talked about here at the conference in a couple of different talks, and that's CXL. We find CXL to be very interesting, and the ability to then have a cache coherent fabric where, say, the CPUs, a pool of CPUs would be an orchestration layer to a fabric of accelerators that do different kinds of transforms and work that then talk to a separate fabric below of storage devices. And they all can then talk coherently to each other through mechanisms that have yet to be defined, of course, but we find that a much more interesting concept for doing disaggregation going forward.
Any comment?
I'll add one more comment. Since open channel is one way to address the drive, another way is NVM sets and endurance groups. This is something which there have been many TPs have gone through NVM Express, and we think that's a much more interesting way to address the drive and partitioning between applications and allowing performance and sharing of drives. And there have been many TPs that have gone through NVMe Express, which are integrated into 1.4, and there's one more left outstanding. It's a work in progress. So,
Okay, thanks. And one last question, I guess, for Lee. What are you brewing in your craft beers right now?
So it's summertime, so it's my pale ale.
Pale ale. All right, beers, a round of beers on Lee Prewitt. Any other questions?
Fly to Seattle.
Yeah, you have to go to Seattle to get it. But he'll personally serve you a craft beer. If there are no other questions, please round of applause for Ross and Lee. Thank you, guys.